So in this lecture, I want to continue our discussion of cycloaddition reactions and move into the next category, which are dipolar cycloaddition reactions. Now, actually, in many cases, these are called 3+2 cycloaddition reactions. And interestingly, some members of the community hate one of these terms over the other. And so I'll just share them both with you. So some people hate 3+2 cycloadditions. Some people hate dipolar cycloadditions. I'm not, yeah, anyway, we'll just include them both and note that these are cycloaddition reactions typically between alkenes and 3-atom dipoles. So alkenes, here we have our 2 atoms, and sometimes these are called, under these circumstances, dipolariphiles. I believe I have that spelled somewhat correctly. So 3-atom dipoles would be like A to B to C, and then there's some sort of charge, permanent dipole charge here, and then there's often a pi bond at some point in those 3 atoms. So let's look at some examples of dipoles. We could have azides. So azides, which I write as Rn3, these are actually in a Lewis formalism considered to look like this. Is a pretty potent resonance structure, but alternatively, we could have this resonance structure. And I feel like the second resonance structure more accurately describes the behavior of azides, but these two are resonance structures, and then we have a permanent arrangement of charges amongst these 3 atoms. So anyway, the internal nitrogen centered between the R group and the center nitrogen, that's always, in many cases, is positively charged, in many depictions is positively charged, that is most often the nitrogen that possesses the negative character. That is this one. Okay, so azides are an example of a permanent dipole. We actually looked at the sort of this dipole previously from a cyclohexanone. So we have a plus minus. Now that doesn't seem to be between the 3 carbon atoms, but all we have to do is consider a resonance structure of this. We move the negative charge down and over. And then now we have a plus minus. So here are some permanent dipole systems, some permanent plus minus systems. And we can just let these react with dipolariphiles or dienophiles, as I often think of them as, because it's typically the same reagents that we use in a Diels-Alder reactions. So we say 1, 3 permanent dipoles. They often just react with alkenes. And so the reaction looks like this. We take our dipole, and I'm going to pick the system shown here. And I'm going to let that react with our alkene, where the minus adds and then the double bond comes over. And we've got our new bonds forming between these 4 atoms. And this often gives rise to a 5-membered ring. So you typically look for which 5-membered ring can you form. And that gives us this as a product with these new bonds. Now, I really like these reactions, no matter what you want to call them, because 1,3 dipoles have the opportunity to introduce a lot of variety, and these reactions actually work pretty well. So because 1,3 dipoles can have many atom types, you can form a large range of products. So I show an example here where we have a carbonyl present, but if we consider like something with nitrogen present, now a nitrone is an example. So nitrones are kind of interesting functional groups because we have nitrogen bonded directly to oxygen. And in this case, we have the nitrogen neutralizing the negative charge in the oxygen by having usually 4 bonds attached to it to give it a plus formal charge. But we can consider a resonance structure that allows us to easily see, more easily, at least compared to the previous example, where the plus minus are that will add to an alkene. And the reaction looks like this. We get our 5-membered ring now with a nitrogen oxygen bond. So we have one carbon from our dipole that's being added, and it's always good to make carbon-carbon bonds. But we now have carbon oxygen bonds being formed, and then an interesting nitrogen oxygen functional group present. Okay, now I said that azides were good examples of dipoles in these 3+2 dipolar cycloaddition reactions. It turns out that azides can react very efficiently. Let's just get rid of the can. React efficiently with alkynes. This is often called click chemistry. The idea behind labeling this as click chemistry is that it's so easy, it kind of works at the click of a button, I guess. I don't really know. I've never understood the choice of the word click, but this chemistry is very powerful, and with the proper choice of catalyst can happen at incredibly dilute conditions. And it's like, why would you want to run a reaction diluted? Because that just means more solvent waste. Well, if what you can do then is do this reaction inside biological systems with only very small amounts of your chemical reactants, which could be useful if you want to do controlled scientific chemistry, that is things that we design in the lab, inside of a living organism for imaging purposes, as an example. And so what this looks like is if we take phenyl azide, which is equivalent to this resonance depiction as a Lewis dot structure. And we could consider this as being in resonance with this depiction. It's probably hard to see what's happening here. So I'm going to go here to here. Add another lone pair on the leftmost nitrogen. We keep a positive charge at the rightmost or at the center nitrogen. I'm going to just push another pair of electrons inward to get us to neutral in the middle, negative on the left, and now negative on, or +1 on the right, because we've lost a lone pair of electrons to the central nitrogen. We cannot move nuclei, so we're still linear about these 3 nitrogen atoms. But now we can see the plus minus separated over 3 atoms, which can allow us to react with something like an alkyne. And this is a reaction that's promoted to occur very quickly, like exceedingly quickly, with copper being present. So oftentimes people will add a copper catalyst, and I believe that forms a copper alkyne intermediate with chemistry we'll talk about during the course of chapter 6, but you get this as your outcome. So just like the dihydrodealzalda reaction, we're going to have a pi bond left over between the 2 carbon atoms that were once the dipolarophiles. So I show that as This double bond is just one of the double bonds that's left over. We only use one of the pi bonds to do the cycloaddition reaction. I have my phenyl group over here. Now, what does the nitrogen system look like? Well, we just connected plus to minus, so we still have a double bond between these two nitrogens. Now, it turns out we have a lone pair accessible to overlap within the pi system. If we need it, remember, we can use those electrons to overlap in the pi system to give rise to an aromatic molecule. So we form an aromatic, what's called a triazole. And so this is click chemistry. So you can attach super interesting molecule to either the alkyne or the benzyl azide and get a biological organism to take up and actually incorporate molecules with the other functional group and do some click chemistry in there. And I've seen incredibly remarkable imaging techniques taking place of actual living organisms, allowing you to get much deeper into the biological system. Okay, so I just got done teaching this reaction in organic chemistry 2. It's one of my favorite reactions because in grad school it was just sort of a blast to do, but that's the ozonolysis reaction, where you basically take an alkene plus O2 in the presence of a lightning storm to make O3. Now, O3 is ozone, and if we want to do stoichiometry, we've got 3 of these, we've got 2 of these, which reacts, the ozone reacts with the alkene to form 2 carbonyls, and we use DMS, that's a DMS, to make carbonyl 1. I'm going to write that upside down just so maybe you can remember how we solve these problems. We draw little O's inside the double bond, break it in half, and then split the carbon-carbon double bond apart. Anyway, fun stuff, plus DMSO to absorb the third oxygen from ozone. So how does that work? Well, you first do a dipolar cycloaddition reaction, or a 1,3 cycloaddition reaction. 2 plus 3 dipolar cycloaddition reaction. 1,3 dipolar cycloaddition reaction because they're separated by 1 and 3. Yeah, okay, all the names. So uses a dipolar cycloaddition reaction. Let's just go right to the chemistry. All right, so let's consider O3 as a Lewis structure. So we typically have plus here, a lone pair of electrons and that's in resonance with plus and minus. And you can put the plus and the minus on either side. It's a symmetric molecule. But then what we could do is just consider an alkene reacting just like any other dipolar cycloaddition reaction to give rise to a 5-membered ring intermediate. And this is a super unstable peroxide. If you look, there's a lot of oxygens around there. And so what you do is you add DMS to this, which is this molecule. I won't go through the full mechanism. I just wanted to show you the dipolar cycloaddition reaction to give us our 2 carbonyls plus DMSO. Okay, it's a pretty cool mechanism though, but let's not make videos longer than they need to be. Okay, so we start with the dipolar cycloaddition reaction to make the unstable peroxide intermediate. Then critically, when the reaction turns blue and we're saturated with ozone, that's when we want to stop the electronic discharge, push out the excess ozone, replacing it with preferably an inert gas like nitrogen, or at the very least, oxygen that hasn't been converted into ozone. And once the blue's gone away, then we add our dimethyl sulfide. It stinks, but it oxidizes and takes care of the unstable and explosive intermediate. Turns out that I've TA'd in a class where they do ozonolysis. It's a really impressive class. And then there's one year where the students weren't really always pay attention to your pre-labs. One year where the students were inadvertently avoiding the use of DMS, they just forgot to add it. And then they put their reaction mixtures on the rotovap, which is what you do. You know, it's kind of like, oh, it doesn't smell as bad today because there's no sulfide present in there. Well, that also means there's a bunch of unstable explosive peroxide that hasn't been reduced yet to the carbonyls. And so when you put it on the rotovap and expose it to the heat from the equivalent of that little water bath that we had about 40 degrees, that was enough to pop the, even under vacuum, explode the contents of the vessel. And so you get some flying glass. Luckily, I believe nobody got hurt. So, you know, follow directions, listen to your pre-labs, that sort of thing. Okay, the next reaction we're going to do is the heliotropic. Awkward word to say, awkward arrows to push, heliotropic reaction. This is a 1+2 cycloaddition reaction. I believe I called the dipolar cycloadditions 1,3 cycloadditions. It's not because it's 1+3, it's because the dipole was scattered across 3 atoms. So you have a 1 atom and a 3 atom, and both of those atoms have charges, but not necessarily the 2, even though in some, anyway, moving away from that nomenclature, this is literally electrons from 1 atom add to the 2 atoms of a pi system. So the 1 is typically a single atom. And so what we need is a single atom to be sufficiently reactive to have both that positive and negative charge character. Well, that's going to come from our carbenes and perhaps nitrines that we've looked at. These are, I like carbenes the best for this this type of reaction. And that's because we can just draw them with the plus and the minus. And this would be dichlorocarbene. Or we could draw them as having a lone pair. And it's technically neutral, although it's just a little bit awkward. But the plus and the minus allows us to see how this can react with a carbon-carbon double bond to make, in this case, a cyclopropane. That is, if we have our double bond present, we can take the minus down to the double bond and then take the pi electrons that just got attacked over to the positive charge, and that's going to give rise to our 3-membered ring intermediate. So this is a cyclopropanation reaction. Now, a discussion of cycloaddition reactions would not be complete if I forgot to include retrocycloaddition reactions. So retrocycloaddition reactions are where you just go backwards. So we've looked at this before. We've seen in the context of electrocyclic ring opening reactions, you could say that's a retro-electrocyclization reaction, but nobody says that. Okay, I mean, that's examples of retro reactions. Here we're looking at cycloaddition reactions, which again are different from electrocyclization reactions. So ignore the ring opening stuff from before because we're talking about cycloadditions, not electrocyclizations. So what does that mean? Well, what it means is I could take a structure like this, and we could heat, we really have to heat this up quite a bit. And this will undergo a retro, and I'm going to call this a DA reaction, a retro Diels-Alder. So in a retro Diels-Alder reaction, you take the arrows backwards, take the double bond over to make a new double bond, and then one of the single bonds over to make a double bond on the dienophile, and the other single bond that was made over to make a the other double bond of a diene. Reminds us what's so great about the Diels-Alder reaction, to spend 2 pi bonds to get 2 sigma bonds, energetically very favorable. So if we want to go backwards, we have to apply a bunch of heat to this, but this allows us to get back to in this case, our 2 starting materials of a Diels-Alder reaction. And if one of them boils away, that's how you can achieve, in this case, this diene, that's how you can achieve the reaction at all, is if you can heat it up so high that any equilibrium content that forms, we can lose a little bit of the reactant through just evaporation. That'll use Le Chatelier's principle. We can then use Le Chatelier's principle to drive the reaction forward. Sometimes people use this as a little bit of a protecting group for alkenes, which has always been kind of interesting to me. This is also the reason why the exo rule dominates, or exo products can form under high temperature. That is, if you remember, the endo product of a Diels-Alder reaction is more sterically hindered and thermodynamically less favorable. So the universe doesn't really want to form endo products, but they're very fast to form. But if you apply heat to the reaction, you shrink the energy gap between the two products, and you also induce any endo product that would be formed actually reverts back to the starting materials and ultimately gives rise to more of the exo product. So the fact is you can achieve reversibility even for a Diels-Alder reaction, which is kind of interesting. Okay, last example we'll talk about for retro reactions are retro heliotropic reactions. These are hard to come by, but when you can use them, they can be quite helpful. So for example, we could take this mostly harmless molecule, and we can apply heat to it to get two very problematic molecules. That is, what I'm going to do is, instead of drawing it as this awkward three-dimensional structure, I'm going to go to the top view. Oops, I've got carbonyl. Go to the top view, and I'm going to do a retro Diels-Alder reaction, or excuse me, a retro heliotropic reaction, where it starts to look like a Diels-Alder reaction, but then I'm going to push the electrons onto a single atom, and then use the electrons on the opposite side, the single atom being the carbonyl. I'm going to use the electrons on the opposite side to form another double bond. So we actually don't break any of the bonds in the wider ring, but in the 5-membered ring, we break both single bonds. That's going to give rise to carcinogen 1, benzene, plus this carbonyl with only a lone pair attached to it. Looks like a carbene, technically is formally neutral at the carbon atom, but a prominent resonance structure is where you take the lone pair down, give everything an octet, but now you've got some separation of charge, which is less bad than things having no octets. So a nice contributor is the structure on the left, but this is carbon monoxide. So this can be a helpful way to generate carbon monoxide during like in situ within the reaction, as opposed to handling gas cylinders. Probably handling gas cylinders is a little bit easier, but it's a super cool reaction because, driven by the force of aromaticity, you generate an aromatic molecule, benzene, and extrude molecule of carbon monoxide. And this is a very thermodynamically favorable process. And so just a little bit of heat can probably get you over the activation energy to form these two substrates. So I'll do it for this lecture. Retro reactions to close it out. Heliotropic reactions are awkward, but we saw both a forward heliotropic and a retro heliotropic reaction. So hopefully this arms us with a lot of information to get through chapter 4. I'm going to go through some more examples in the subsequent lectures.